Okay, IED, we're just going to take a little bit of time to tie up some loose ends about Activity 2.1.1, tolerate this. There are a couple of concepts and things that I haven't really talked about yet that are going to end up being useful to you guys when dealing with not only this section but other sections in the future. We've done the 3D printed block exercise, so if you haven't checked that, check out the other video in the playlist. But the way that it turns out is that if you're going to make multiple things, like say if you had a part and you wanted to make like 10, 20, 30,000 of them, and you counted every single one of them and you dimensioned every single one of them, if you were to make like a dot plot or a box plot or a histogram, what you can find out is you can find out the shape of the distribution of the objects. And what I'm really talking about here is that the average is going to be this spot right in the middle. So let's just pretend that we said that okay, well we're going to make some blocks, and the blocks have to have a dimension of 2 inches. So if the average is 2 inches, what we're seeing right here is we're seeing the deviation away from that 2 inches. And what normally happens in real life whenever you make stuff is that sometimes those objects will be a little bit longer and sometimes those objects will be a little bit shorter. So instead of being 2 inches, 2.000 inches, it might be like 2.001. And the further away you get from the deviation, the more intense that deviation gets, the further away from the mean we get. So really what we're talking about here with a normal distribution, and by the way, whenever it says normal distribution, this is this bell-shaped curve. It kind of looks like the end to a trumpet or a smooth mountain or something like that. This is called a normal distribution, and we call it normal because of how often it actually shows up in real life. It is literally a normal distribution. There are other different types of distributions, but we're not touching those with the 10-foot pole, so let's just kind of move on. Here we go. Now, the standard deviation we've talked about before, the standard deviation is roughly how far away you are away from the average itself. So whenever you see this 1, 2, 3, 4, 5, this is how many standard deviations you are away. And to best explain that in terms of numbers without using a mathematical formula, if this object is 2 inches right on the dot, if the standard deviation is plus or minus 0.05, then the standard deviation, each time we move up a standard deviation, we would move up 0.05 inches, which means that it's very, very likely for an object to be plus or minus zero point zero 0.05 inches from this object. But if you were to go another standard deviation and say, well, okay, that's going to be a tenth of an inch off, then it becomes less likely. And the further away you get, the less likely it is for you to get these really big errors that occur until you get into like 4, 5, and 6 standard deviations. And if you get to 4, 5, and 6 standard deviations, in terms of manufacturing, something is very wrong with the part because you shouldn't be deviating this far away except for very rare or extenuating cases. So, if we're talking about like percentages, 68% of your data is going to fall within one standard deviation. So plus or minus from this spot to this spot, from +1 to -1, 68% of your blocks that you create are going to go within this area. And 95% of all of the blocks are going to go within two standard deviations. So what that means is that it's +1 +2 standard deviations and -1 -2 standard deviations. So all of this area right here between +2 and -2, all of the data, 95% of your data will be within two standard deviations. If we're using the block example, it would be plus or minus zero point 0.10 because one standard deviation is 0.50. So 95% of your stuff is going to be within 0.50, or sorry, within 0.10. Another one that I try to use is the argument of oil changes. When you get a car, when you guys start driving, you're going to find out that they ask that you do an oil change every 3,000 miles or 3 months. And the reason why they do that is because they know that it is very, 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 very unlikely for you to have mechanical trouble. So it's several standard deviations away if you change your oil every so many miles. And I think it's 3,000 miles or 3 months. So they know that, there's almost no chance of any mechanical mess up. But if you let your car go for 4 months or 5 months or 6 months, your chances of actually having a mechanical failure increase as you continue to go. And if you haven't had your oil changed in like years, it becomes even more important to get that oil changed because you might run into a problem just specifically because you haven't oiled the engine in your car. So they do that basically based off of data and standard deviations. So most people have probably found out by now if you don't change your oil within 3,000 miles, it's not going to instantly like catch your engine on fire. But it's more of a guideline that you want to get it done because at 3,000 they're basically like, yeah, these chances are so low that you're good to go at this point, and we can safely say that your engine is fine because of the oil. Anyway, here's what the standard deviations would look like in terms of the amount of data. So once you get into plus or minus 2 standard deviations, you can see there's a big, large chunk of your data is going to end up in this area. And then it tapers off very rapidly towards the end with plus or minus 3 standard deviations. Anything past that, 4, 5, 6 standard deviations, I would call an anomaly. It's going to be it's an outlier. It's not going to be a large amount of data in that spot. Okay, so and this is what they call the 68, 95, 99.7. Sometimes you hear it called the empirical rule. As an engineer, I don't really use the term empirical a lot. That's for scientists. So keep that in mind if you hear the word empirical rule. Oh, statisticians use that all the time too. So keep that in mind too when you're talking to a statistician. All right. So let's see here. We did the thing with the dowel rods, and we did the things with 3 different types of fits. The big two that we're going to be seeing is clearance fits and interference fits. Transition fits have rare importance in at least the stuff that we do, because we either want it to stick together or we don't want it to stick together. So we either want it to slide across or we want it to not slide across. Transitions are a little bit tricky. I'm not going to worry much about those much at all. So there's some more questions to answer whenever we get down to here. Um, let's see here. I think there was one more thing that we wanted to do. Okay, yeah, the MMC and the LMC. Sometimes you're going to see the words MMC and uh, LMC. MMC stands for maximum material condition, and that is the condition of a part when it contains the largest amount of material. And the least material condition is going to be the condition of a part when it contains the least amount of material. So if you are, it says here are a couple of examples. The MMC of an external feature, e.g. the length of a plate or the diameter of a pin, is the upper limit of the dimension. So the maximum material condition of like a dowel rod or something like that would be the longest or the length of the plate itself. Okay. Um, so if you're dealing with, let's see here, if you're dealing with a internal feature like a hole, that's going to be the lower limit of that dimension. So I think some pictures are going to be in order here whenever we talk about MMC and LMC. I might need to make some 3D printed stuff to, or at least some on-shape stuff to actually show you the three-dimensional stuff. Now notice that it's going to be backwards for the least material condition. So if you're doing the least material condition, if you're using like a stick or something, then the actual length of the stick would be the lower limit. But if you're dealing with something like a hole, then that's going to be the upper limit of that diameter dimension. So I think some 3D models are in order. So I'm going to try to make a video on MMC and LMC just to show you guys, because I really do think in this case a picture is worth 1,000 words. But I think that's really going to wrap up the tolerate this. So try to look for that video, and I'll talk at you guys later.